All right, everyone, welcome back. We have 4.3, transforming radical functions. Now, your learning goal is to use transformations to graph radical functions. So in a previous video, we used transformations to graph quadratic, and we're going to be doing a lot of that same stuff except for applying it to radical functions. Now, the two radical functions we're going to be focusing on is the square root function and the cube root function. Now, let's first start and talk about the parent function here, okay? Now, we know a couple details about when we take the square root of a number. For starters, we know when we take the square root of a negative, in fact, let's not use 2, let's use 4, we get a number like 2i, and that's not really visible on a coordinate plane like this. This is a coordinate plane for real numbers. Now, there are ways to graph imaginary numbers, but we don't really see them here, okay? So what you're gonna notice with this square root function here is that we can't input any negative values. So all these values over here can't be inputted for the parent function. Now, obviously, if we shift things, we subtract some stuff within the radical, that could change, but for the parent function, we can't put any of those in, okay? So we're gonna use a table, and I'm just going to use the numbers. Let's go with 0, 1, 2, and let's just do 3. Okay. Actually, you know what? Let's not use those numbers. Let's do 0, 1, 4, and we'll throw a 9. Okay. 0, 1, 4, 9. And you're probably seeing why I'm using these numbers all of a sudden. When I chose 2 and 3, well, when we take the square root of those numbers, we get a very intense decimal. So I'm using ones that we can easily understand when we take the square root. From this point on, these are the 4 that you should use as your parent function inputs, okay? Obviously, when we take the square root of 0, we get 0. When we take the square root of 1, we get 1. We take the square root of 4, we get 2. And we take the square root of 9, we get 3. So we go to plot this, which I'll do in red. And we have 0, 0, 1, 1, and then let's go out to 4, 2, and all the way out to 9, 3. And you should see, let's try it again. Let's try this again. This, okay? Notice that it's just half of a curve here, right? Like it looks like half of a quadratic point to the side. That's exactly what a square root function should look like when you graph it, okay? It shouldn't be visible through the whole graph because, again, we can't input those negative numbers so easily, okay? So this is your parent function. This is the most basic square root function that you can have, and these are the 4 points I want you to use as your parent function, okay, for transforming. All right, now before we actually go and do it by hand, we're actually going to shift this over to Desmos for a second so that we can, kind of quickly look at what happens when you change certain details, okay? Okay, so now you can see we're in Desmos. We have our parent function here, starts at 0, 0, and, we can trace off and see those numbers, right? We had our 9, 3, our 4, 2, our 1, 1 right around there. And let's start to see what happens when we change this function, right? Let's just add a number to the outside. Let's just add a 4. And you can see same thing, everything just gets shifted up 4 spaces. Okay, so now it's not 1, 1, it's 1, 5. Sorry, it's kind of hard to get it right on that point. Okay, now if we minus that 4, same thing, it goes down. So just like your vertex form of quadratic, when you added or subtracted that number on the outside, it just goes up or it goes down. Okay, all right, now let's look inside. What happens if we add or subtract a number inside the radical? Okay, so let's do a plus 2. Now notice how it moved 2 spaces to the left, okay? And this actually starts to make a lot of sense when you think about it, because before we said you can't plug in negative numbers into the parent function and get it on the graph, but now you can see we have negative inputs, and it's because they're being canceled out by that plus 2. If I input that point, negative 2, 0 there, right? And then the first thing I do is add 2 with it, it brings me back to 0. So again, this is extremely similar to your vertex form of a quadratic, okay? So it's a little opposite. When you add inside the radical, you go to the left. And when you minus inside the radical, you go to the right, okay? All right, now let's look what happens when we start doing things to the outside. See, we multiply 2. You can see that we kind of have our stretch there again, so it's stretched out. And then if I do a -2, it flips, right? So now it's going down instead of going up. And let's do a fraction. 1/2. Oops, we got to get that 2 there. So I got to cancel out the other 2 because that would just be 1. And there we go. It shrunk or compressed, however you want to call it, okay? So what I'm getting at here is that your transformations of a square root functions are almost identical to your vertex form quadratic transformations. You're just dealing with a different function, okay? All right, we're going to go back to our stuff here, okay? And we're going to start doing this by hand. Now remember, we have our parent function at 0, 0, 1, 1, 4, 2, and then 9, 3, okay? And so here's our parent function, which actually, sorry, I'm not going to do anything with that right now. In fact, I think we used x's for these in the past when we wanted to transform them so that we didn't get them confused with our actual one, okay? Now, we can really do these in any order. I'm just gonna do, my up or down, and then my left or right. You can kind of do that however you want. So I see we have a -3, so that's right 3. I see we have a +2, so that's up 2. In fact, why don't we just do these at the same exact time, okay? So I'm gonna take each point, I'm gonna go right 3, up 2. So that puts me here for kind of like our vertex, our first point. So 0, 0, went over 3, up 2, okay? Now remember, we -3, so it's the opposite. You think that would be left, but that's really right, okay? The next one over 3, up 2, over 3, up 2, and then that one would go off the graph. And so, normally we would adjust that, but with this graph here, we don't actually have that visible range, so that's okay. We can just draw it out like that, okay? And that would be it. So let's do another one, okay? And let's do one with a little bit more stuff going on, okay? Let's first analyze what our transformations are. We have a -3, so that's down 3. We have a +2, so that's left 2. And we have a 1/2, so it's compressed or shrunk by a factor of 1/2, okay? So let's take that into account. We're going to deal with the 1/2 first. So I plot my parent, 0, 0, which I'm going to do in x's, 0, 0, 1, 1, 4, 2, 9, 3, okay? And now I'm going to go and I'm going to take half of all those numbers. So half of 0 just puts me back on 0. Half of 1 puts me here at 0.5. Half of 2 puts me at 1. And half of 3 puts me at 1.5. Okay, so you can see really there that it compressed. Okay. Now I need to move the left 2 down 3, which we're just going to do in one step, and I'll do it in green. So I'm going to take all these points. I'm going to go down 3, left 2. So down 3, left 2, down, did not go down 3. Look at that, I saved the day. Down 3, left 2. Okay. You guys are all probably getting those comments ready, huh? Down 3, 1, 2, 3, left 2. Down 3, 1, 2, 3, left 2. Down 3, 1, 2, 3, left 2. Okay? And it's going to go out like that. Okay? All right. Now, again, very, very similar. I'm going to have you guys do one now. In fact, what I realized that I'm missing here is that we need to talk about our domain and range before we do that. Okay? So, yeah, that would have been crucial. Okay? So we do need to evaluate all of our possible inputs and all of our possible outputs. So you can see, if you look here, you can see we're not going anywhere to the left of 3, as all the values greater than and equal to 3, or equal to. So we would write our domain as x is greater than or equal to 3. Okay. Our y, on the other hand, we look vertically. We see its lowest point is at y is equal to 2. So it's the same thing. Y is greater than or equal to 2. Okay. All right. So, that one, you actually have to do domain, unlike your quadratic functions where you just did all real numbers. Here, we actually have to do them, okay? Now, same thing here. Our domain. We look at our x's, right? You can see right here, -2. So it goes x is greater than or equal to -2. And then our range, I can see right here, the lowest point is -3. So y is greater than or equal to -3. Pretty straightforward, okay? All right, now go ahead, give it a pause, try this one yourself. Okay, so hopefully you gave this a try. Let's first see what we should do. We got a +3, so we need to go up 3. We have a -1, so we need to go right 1. And we have a -2, so we need to reflect. And it stretches by a factor of negative, or just what we would say, it is -2, stretches by a factor of -2. But I choose to kind of think of that reflection a little bit separately, but it is stretched by -2. Okay, so let's plot our parent, 0, 0, 1, 1, 4, 2, 9, 3. Okay, now we're going to do our -2 first. We're just multiplying all these numbers, these y values, by -2. So 0 times -2 is 0. 1 times -2 is -2. So down here. 2 times -2 is -4. And then 3 times -2 is -6. So you can see that those numbers are now below, and they're much different values, okay? Then the last thing we have to do is we move our up 3 and our over 1. So up 3 over 1. For our first point, up 3 over 1, up 3 over 1, up 3 over 1. And that should be our point. Let me draw that. And notice how I'm not, going past that first point to the left, okay? Now we find our domain and range. We can see here for x, it's going through, the leftmost point is +1, so x is greater than or equal to 1. And then for our range, we see that it doesn't go below +3, and so y is greater than or equal to 3, okay? All right, so hopefully you got that. If you didn't, it's okay. We'll have some more practice. Really think back to your transformation with quadratics, okay? Now we do have another function to go over. This is going to be for the cube root. Now the cube root is going to look much, much different, okay? And we're going to use a different set of points for our parent function, okay? Now think about it, we have to find a number that multiplies 3 times when we're taking the cube root. And so getting those, perfect cubes, there's much more of a spread between those numbers. So we're going to use -8, -1, 0, 1, and 8 because all of those are cubes, okay? Now notice the big difference. We can have negative input for the parent function, and that's totally okay, okay? So if we plug in -8 into our cube root, you get, -2. -1, you would plug it into our cube root, you get -1. And that's because -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. With 0, again, 3 zeros equals 0. With +1, it's all the same stuff, but now we get positive numbers and positive numbers, okay? When we go and plot this, we have -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Now you're looking at these points and you're probably thinking, what on earth does that look like, right? Like, it looks like there's a straight line here, but then what are those other 2 points? And what you get is something like that, okay? So it is kind of symmetrical. Both sides should look the same, but kind of flipped, all right? So if I kind of, let me try and redraw. That's worse. Okay. We'll do a Desmos thing and you'll see, okay? But we get this very interesting shape here that crosses the graph and is flipped on one side, okay? All right, as promised, we'll do a Desmos exploration. All All right, so I totally cut off my last recording while talking, but that's okay. We're going to quickly go over this. As you can see, we get that kind of flipped shape, all right, and that's okay. Let's look at what happens again. You add 4 on the outside, every point goes up 4, right? You minus 4 on the outside, every point goes down 4. I know I'm like being a dead horse here, but I think it's important to see it, okay? Especially, to see it quickly, all right? So we know you add something to the outside. It's a vertical translation, very straightforward. We go to the inside. Let's say we add 2, exact same thing. It goes to the left 2, right? You minus 2, it goes to the right 2, all right? You put a number in front, a positive 2, and we get this stretch, right? So this shape really starts to change, okay? We put a 1/2, let's do 1/2. It gets very, very close together, compression. And then let's add that negative real quickly, and it flips. All same characteristics, okay? And so, if you remember what the parent function is, you remember those points, you're really good for quadratics, for cube roots, square root functions, absolute value functions, for a ton of them, okay? So I know that one was a little bit quicker, but it has all the same types, it just, the function looks different, okay? So let's jump back and let's do this by hand. All right, so here we are. We have f of x is equal to the third root of x minus 2 plus 1, and we're doing all the same things. We see a minus 2 on the inside, so that's right 2. We see a plus 1 on the outside, so that's up 1, okay? So we have a little bit different of a parent function here though, right? We're at 0, 0, we're at 1, 1, and negative 1, negative 1, and then we're all the way at 8 and 2, and negative 8 and negative 2, okay? It's a weird set of first points, okay? But that's all right. So let's graph these, or let's do our transition. Right 2, up 1. So right 2, I'm going to start from the center. Right 2, up 1. So that was this one. Okay, I'm going to do the right points, and then I'm going to go back and do the left points. So right 2, up 1. And then this one over here, all the way to the right, it's just going to go off. I'm going to try my best. Let's see, right 2, up 1. It's somewhere right there. I know that point's hard to see. Okay. And then where are we at here? Our left points, right 2, up 1, and then right 2. Well, we all know I'm not stopping this recording. Okay, I'm too far, way too far in this, okay? Right 2, up 1, okay? Yeah, it's late. There's no way I'm redoing this. Okay, we draw our graph. It should look the same as what it would normally look if I could draw better. It's just all the points are moved to left and right, up and down, okay? All right, we got to do our domain and range. So domain and our range, okay? Now, this is where things get interesting, okay? If you look at the domain and range, you look at this arrow, it's going infinitely this way, and you look at this arrow, and it's going infinitely that way. So your domain is all real numbers. Now, if you think about this, it looks like we're tapering off here, right? Like it looks like we're not going to exceed a certain point, but as we increase our number, that we're taking a cube root of, we'll continue to get bigger numbers. If we take the cube root of 27, we get 3, right? We take the cube root of 64, we get 4. We're just going to keep getting bigger. It's going to be excruciatingly slow, but it still is all real numbers, okay? All right, let's go to the next one, okay? Very, very similar. We have, no up or down. We have a plus 1 inside, so that's left 1. We have a negative 2, so it's reflected. Oh, that was too, wow. Let's redo that. Reflected and stretched by a factor of negative 2. Okay, so I'm going to go and plot our parent function 0, 0, 1, 1, 8, 2, negative 1, and negative 8, 2. okay? And I always do the stretch and compression first. So I'm going to multiply all these by -2. And, quickly you can see that's just going to flip them all, right? If you're down here at -2, it's going to go up to +2, right? And all these are really just going to flip. Pretty interesting, okay? Oh, no. Whoa. Man, I must be getting better. I keep catching myself. Okay, let's do this again. That would have been if I would have multiplied by -1, not by -2. These should flip, but they also should increase in value. If you have -2 here and you multiply by a -2, you should get +4, way up there. If you do -1 by -2, you should get +2. 0 stays 0. +1 by -2 should go down here. And then 2 by -2 down there. Okay, so that's my bad. And then the +1, which means we go to the left 1. So all these points, you're just going to move them over 1. Okay, and you should have this. Okay? All right. Now, I think I got, oh, nope, domain and range, which we know, all real numbers, and all real numbers. Okay? All right, here's the next one. This one's for you guys to do. Give it a try, and then I'll go over it. Okay, hopefully you gave that a try. I'm just going to go and check all these, right? We have a down 2. We have a left 4. And we have just a compression by 1/2. Okay, so we're going to plot our parent function. All right. Okay, and then we're going to first do the compressions. We're going to multiply all these points by 1/2. Okay, I'm going to do that in green. So 0, I'm just going to, well, I did left to right last time. Let's do that. So -2 times 1/2 should bring us to -1. -1 times 1/2 should bring us to a -1/2. 0 times 1/2 should just be 0. 1 times 1/2 should bring us there. 2 times 1/2 should bring us to 1. Notice how, to the left, these 2 points and these 2 points really end up on the same number. It's just one will be positive and one will be negative, okay? Because both sides should look the same, just kind of, reflected across -x, okay? All right. Now, we need to handle our left 2 down, left 4 down 2. Okay, so that's from green, left 4 down 2. Left 4, let's see, 1, 2, 3, 4, down 2. Wow, it's an intense drop. And then that should put us here, left 4 down 2. Should put us here, left 4 down 2. And then this one's going to go off, but we'll just do these additional points. So 1, 2, 3, 4, down 2 here. Okay. And so this one is much closer together because we have that compression. And it should look like that. Okay. And again, domain range, all real numbers. My goodness, all real numbers. Okay. All right. Now, we're going to do one more thing. Okay. So it's going to be a Desvos exploration plus a math talk. What are these square and cube root functions used for, right? Now, this is not going to be the most in-depth example, but this is going to be the start of a conversation. All right, so you guys can see I really have 4 functions drawn on the left. I have an x squared and a square root of x. I have an x cubed and a cube root of x. If you notice, the x cubed and the cubed root are not showing right now, okay? We just want to look at the x squared and the cube root of x, okay? So remember one thing about inverse functions is that, if I have a function that takes me from x to y, the inverse function should take me from y to x. So, if you think about the point, this first point here is 0, 0, right? Well, the flip of that would be 0, 0. And our blue and green function are showing that, right? Let's look at this 1, 1 point. Same exact thing, we flip them, it's the same. Okay, we're not really getting much with that. But let's start to look up here, which is not really giving me 2, 4, okay? But you can see right there, that blue line goes through 2, 4. Well, what's the opposite of that? 4, 2. And you sort of see our green function here crosses 4, 2. Okay? Believe it or not, the square root function and square root function and a quadratic are inverses of each other. Now you're looking at this, go, how are they inverses? They look so different. But if you look at the green line, you start to realize that's half of a quadratic. When you take the inverse of a quadratic, it kind of like, rotates, 90 degrees to the right, okay? And then it's sideways. Now the problem with that is a function has to pass the vertical line test. And when you put a quadratic on its side, it no longer passes the vertical line test. So it's kind of like taking half of a quadratic. So this really only brings us back half of the time, okay? So, again, what's the purpose here is a square root function brings us back, okay? It's the inverse of a quadratic. Now, that doesn't seem like the most beautiful, this is why we need square root functions. And there are more reasons, and I plan to get into them, but this is what we need to know for now, okay? Now, let's close those out, and let's look at what the cube root looks like, or the cubed function, which now you probably already very quickly, after graphing a bunch of cube root functions, are seeing that this is extremely similar, right? And we put that one in. Okay, wow, even an interesting, artwork there, right? Okay. Now, again, I compare the numbers and you're going to see that these are inverses of each other. They don't have that same negative issue because cube roots can take negative numbers, but these are inverses of each other. They help us go back. Now, we have not been using we have not been doing x to the power of 3 yet, and that's okay, but we will be getting to that, okay? So what do you need to know right now? You need to know that the square root function is an inverse of a quadratic, and a cube root function is the inverse of the cube function, which is x to the power of 3, okay? So I hope you guys enjoyed this. I hope that, using the Desmos helped. If it did, please let me know. If it didn't, let me know that too. See you guys next time.